Rn space. Suppose if we take this set, which is a convex set, and this set suppose S, and that S is belongs to Rn space, and this set is suppose convex set. Okay, so this theorem says that if this is a non-empty closed convex set which belongs to Rn, and suppose any point in your Rn space, and that point is suppose outside from that convex set. Suppose there is any point suppose y. Okay, and this y is doesn't belongs to that S. Okay, and say this is any point which is not contained in S, but this belongs to Rn space. Okay, so there is basically infinite number of hyperplanes. Basically, there are infinite number of hyperplanes which passes through this point. Suppose this lab point, and this is in R2 space. You can see that this is your any elliptical set, convex set. Okay, closed convex set, and there are the straight lines that is your hyperplanes. There are infinite straight line which passes through that point y. Okay, so there are infinite hyperplanes that passes through that point y. Okay, so suppose this theorem says that there exists uh, simple hyperplane. So there are infinite hyperplanes, but there exist certain hyperplanes. Suppose we take this one. Okay, this is straight line. Okay, so one of is infinite collection of hyperplane. So we select this one, or you can select another one if you take this hyperplane. Or suppose any student has taken this type of hyperplane. Okay, so this says that there exists a hyperplane H, जिसे हम separating hyperplane कहेंगे, which contains that point y, and such that this S is completely contained in one of the half spaces. If we take this black hyperplane, so this divides this Rn space in two half spaces. So here S is completely lie in one of the half spaces. Okay, like this. Okay, anyone which take suppose this green line hyperspace. Suppose this is, if we consider this hyperplane. So in this hyperplane, this completely divides that R space in two half spaces, and this convex set S is completely lying in one of your half space. So suppose this is lies between this half spaces. Okay, so basically our theorem is that, and this theorem is the proof of that theorem is basically depends on a simple lemma, and we using that lemma and try to prove that theorem. Okay, so here, if we the statement of this theorem says that let S be non-empty closed convex set which lie in Rn, and say y be point which is not in this convex set S. Okay, so then there exists a hyperplane H, जिसे हम कहेंगे separating hyperplane. That hyperplane is called separating hyperplane, which contains that kernel point y such that so that S is contained in S is contained in one of the half spaces, the open half spaces. Okay, which is produced by this hyperplane H, produced by hyperplane H. So this is the separating hyperplane theorem. This theorem is also named by this is a separating hyperplane theorem. And the proof of this theorem is basically based on lemma. So first of all, we write here lemma. Okay, and lemma is simple. This says that if S be closed convex set in Rn and any point which is not belonging to that set S, then there exists there exists a unique point. There exists a unique point, and if we define that point is suppose x naught, okay, which belongs to that set S with minimum distance from that point y which is not belongs to S. So the minimum distance from the point y, that is, you can say that distance means the norm of this distance x naught to this point. So this distance is basically minimum. So this is less or equals to for any x which belongs to that set y. For all x that belongs to convex set S. Okay, so basically this says that if S be closed convex set S and any point y which is not belonging to that x, so this lemma says that there are infinite points in this closed set S, of course in the interior of that, and the boundary points are there. Okay, but there exists a point, simple point. Suppose if you take there are so many points, but at least one point of x naught here. Uh, here this is the distance between these two is minimum. Okay, so if you take for any x which belongs to that set S, so this distance is minimum one when you're taking this distance. Okay, so this lemma says that this external point which now belongs to S, the distance between these 2 points is minimum. That this means this x naught is a point that is a unique point that belongs to that set S. Okay, तो ऐसा एक point आपको जरूर मिलेगा जहाँ से आप बस the distance होगी, that distance is minimum. Okay, so this is a simple lemma. Then we try to prove this theorem. So proof. Okay, so basically okay, so this proof of theorem, and if we take this is question number 1 because we using that lemma. Okay, so here if you assume that S be non-empty closed convex set, and here we take this y is non-belonging to this set S. Okay, so if we take this as y be not a point in S. Okay, so we starting with that. So Hence, by our lemma, we say that hence by our lemma, or you can say simply question number one, or question first. Okay, so there exists some point. So in our lemma, we consider x naught point. So in our theorem, we take this point is suppose any arbitrary point. So we take suppose w. Okay, so there exists a unique point. There exists a unique point, and that point is say if we take w, which is belongs to your s, which is closest to this external point y, so closest to y. So that this means to take to this convex set S, okay, and this is closed convex set, and here your point is y. So by lemma, you take a point. There exists a point. Suppose this point is w, which belongs to that set S, such that this distance is minimum one. Okay, because there are certain lots of point here, and or if you take any point, suppose x here, which belongs to that set x. Okay, so the distance between this y minus w minus y is less or equals to this x minus y. So this means you can write this is uh, in this form. This distance is minimum means the distance y to w. This distance is less or equals to any x, okay, equals to when this arbitrary point x, if you consider the same point w, then in that sense these 2 points are these two distances are same. Or in other words, you can also take suppose this type of uh, closed set S, and if you take here this point y, okay, so this means there are this thing, okay, so this distance is always minimum one. Okay, so this is basically perpendicular distance. Okay, perpendicular distance. Okay, so are you take any certain, if you take this type of structure, this type of structure, okay, and you say that there are two different points. This one here distance is also minimum, and here distance is also minimum. Okay, but this type of structure, this set is not convex, because if we to take 2 points from here, so this set is not convex. That's why if you take a closed convex set, there exists a point that distance is minimum. Okay, so here this distance is minimum. This means x minus y for any x which belongs to s. Okay, so for all x which belongs to that closed corner set s. So this is equation number two. Okay, so since you know that for any x that belongs to convex set, so the point, if we take the convex combination of these 2 points, if we take this, this is your point w, and this is for any arbitrary point of this set x. So suppose we take this point. So this means this convex combination of these 2 points, this will line valuing these 2 points. Suppose this arbitrary point is z. Okay, so the point which we say this point is z, and that is the convex combination of these 2 points, means theta and 1 minus theta of another point, suppose w. Okay, and where this theta is lies between 0 and 1. Okay, so this arbitrary point z, this arbitrary point z is also in those set S, because this S is convex set, and W and X are the 2 points belonging to that set S. So any convex combination of these 2 points is also belongs to that set S. Okay, so you can say that this point Z is also, this point S is also in convex set S. So we have we have say that that distance is also belonging because the z is also belongs to s. So this distance w minus y is also less than the z minus w. Okay, so this means we know that this distance is minimum one. So this is less or equals to for that point also. So this means z minus y. Okay, because the z is also belongs to that set s. Okay, so here, okay, so we can now use this notation and try to solve this value. Okay, so or you can write down this equals to simply norm of w minus y. This is less or equals to what is theta here, theta z here, z is theta of x, this thing. So you can write norm of, we putting the z value here, theta of x plus 1 minus theta of w minus y. Okay, so norm of this. Okay, or you can this equals to, you can if we solve this, so this becomes if you take theta is common here, this becomes x minus w minus y. So we can take here w minus y, and plus if we take theta is common, so this becomes x minus w. Okay, so this means norm of this is less or equals to this term. Okay, so either you say that this is also equivalent to, okay, so on next page, next page is write this is greater than this term. Okay, so we can write this term norm of w minus x plus theta x minus w. This is greater or equals to this term. Okay, so next page we write, so this implies we can say that is norm of w minus y plus theta times x minus w. This is greater or equals to this w of minus y, the w minus y. Okay. And this is equation number 1, 2. So this is 3. Okay. So here we have then we can write uh, this term as this equals to norm of this. This means you can write this minus w plus uh, this theta x minus w. This transpose with w minus y plus theta x minus w. This is greater or equals to this x minus w minus y transpose, and this is w minus y. So you can write this equation 3 as like this. Okay, so okay, so now if we try to solve this equation, so here you get uh, uh, this transpose with this transpose plus theta with the real one, this transpose to this transpose, and if you multiply here, so this becomes w minus y transpose, and this into w minus y plus theta is common, then x minus w transpose here w minus y, and okay, and this transpose here. Okay, first of all we multiply this into this and this into this. Okay, so okay, so we can write this multiply by this to have theta be the real one, so this becomes w minus y transpose and x minus w, and then we multiply second one, so it becomes theta, and this is x minus w transpose and w minus y, and then theta square x minus w, okay, transpose and x minus W. This is greater or equals to this transpose and W minus Y. Okay. So here, use the here this is W minus Y transpose W minus Y. So this term and basically this term both are same. So this term and this term are same. So if you these two are cancelled out, so simply this equals to theta square. Simply this equals to theta square and x minus W transpose and x minus W, that's theta W minus Y transpose and x minus W, that's theta x minus W transpose and W minus Y. This is greater or equals to 0. Okay, so this is greater or equals to 0. So here you can rewrite this term as a theta square, and this is x minus W transpose, and this becomes x minus W, and this becomes theta and theta. This becomes 2 theta W minus Y transpose and x minus W. This is greater or equals to 0. Okay. So because these two terms are same, okay, if we uh, why these two are same? Because you know that A transpose B, okay, A transpose B whole transpose, if we take in this term, so this becomes B transpose A. Okay, so this term. Okay, so here if we take this transpose, if we taking here A, suppose this is A transpose and this is B. Okay, if we're taking the transpose of that, this transpose and this thing. Okay, so you know that these two are same. So that's why these two are same. So here this is 2 times of this thing. Okay, so now okay, so you know that this theta is lies between 0 and 1. Theta is lies between 0 and 1, and this is x minus W transpose x minus W. This is the norm of x minus W square. Okay, norm of that. So this becomes your positive one. This becomes positive one, and plus this is 2 times, and theta is either greater or equals to 0. Okay, and the sum of these two is greater or equals to 0. This implies this term is also greater or equals to 0. Okay, so this implies you can write this term. This implies you can write here this W minus Y transpose and x minus W. This is greater or equals to 0 because this x minus W transpose x minus W, that is the norm of x minus W. Okay, so this equals to uh, this is greater or equals to 0, and your theta is also greater or equals to 0. Okay, so this implies this term is absolutely greater or equals to 0 term, and here theta is also greater than 0. This implies this term is greater or equals to 0. Okay, so this means we can say this equation is suppose equation number 5. Okay, this is 3 and this is 4. Okay.
हेलो सर।
हाँ,
सर वो इक्वलिटी को आपने कैसे होल्ड करवाया और एक बार बता दीजिए ना। 2 थीटा ऑफ दैट वो जो किया आपने, मतलब W माइनस Y द ट्रांसपोज इनटू X माइनस W इज इक्वल्स ऑफ दैट सेकंड
ये
पार्ट।
ये
हाँ
दोनों इक्वल
हाँ हाँ,
कैसे हैं? ये दोनों इक्वल कैसे हैं?
यस सर, यस।
ओके 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 ओके। अच्छा, ओके, suppose if you take a vector, that a vector is suppose a1 a2 a3. Okay, and suppose any b vector which is components are suppose b1 b2 and b3 component, these two are in R3, huh? So This means if we try to find what is the A transpose B, A transpose B means this is A1, A2, A3, and this is multiplied by B1, B2, B3. So this equals to summation of AI, BI, where I equals to 1 to 3. Okay. Similarly, if we take this B transpose into A, so this is B1, B2, B3 with multiplication A1, A2, A3. Okay, and this is also equals to summation of I equals to 1 to 3 AI, BI. So this means, uh, okay, this is a BI, and if we take this transpose of that, okay, so this is also equals to your uh, B transpose this thing, A transpose this thing. If you multiply, this is BI, this is B transpose A, okay, summation of that. And if we take B transpose A whole transpose, so this is equals to summation of AI, BI, I equals to 23. Okay. Or you know that this any vector A transpose B, this whole transpose, this equals to B transpose and A transpose transpose. Okay, so this equals to B transpose A transpose transpose, that is A. So that's why these two are equal. Okay, so here we take this vector. This vector is suppose if you're taking any vector, suppose if you take this vector, suppose this vector is A, okay, and this vector is B. Okay, so what is the value of A transpose B? Okay, so A transpose B, and if we're taking the transpose of that, if we're taking transpose of that, so this becomes B transpose A transpose transpose. So this equals to B transpose A. And what is your B transpose? B transpose means X minus W transpose, and what is A here? A is X minus W minus Y. So that's why these two are same. Okay, because this is A, this is B, this is A transpose B, and this becomes your B transpose, and this is your A. Okay, so you get here A transpose B, A transpose B is equals to, this is, you get here, finally, you get here, this is your A transpose B, and this term is B transpose A transpose transpose, that is B transpose A. Okay, so that's why here both terms are same. So we take the terms are same, we take two times of that. Okay, so this is also zeta equals to 0, and theta square is also zeta equals to 0, and here theta is also zeta equals to 0. That's why this term is also positive. Sum of two terms is positive one, so that's why this term is also zeta equals to 0. Okay, so here next one, since y is any given point. Okay, so in fact this is your closed convex set x. Okay, and here any point which is w, which is belongs to your convex set s, and here there is a point y which is not in s. So you say that there exists a hyperplane that that divides this Rn space in two half spaces, and this open set, this closed set, convex set S is completely belonging to one of the open half spaces, either this one or this one. Okay, तो यहाँ पे हम ये लेके चलें, since this point y, since this y is a given point, is given point which is not in S, which is not in your set S, and W is a point it belongs to this S. Okay, and if we joining these two, uh, this is also point, this is also point, and if we joining this point, so this is also a vector. Okay, if you take this final point position and initial point, so this is a vector A. Okay, if you take this position vector, this W minus Y, so this is a vector basically. So here, if we take that W minus Y, that vector is supposed to be take here A. Okay, so if we take this A with a vector, and that is W minus Y. Okay, so this is a, because this is a fixed point, so this is a your given point, this is a known point. Okay, so you have known this point, and this is also you have taken this fixed point. So these two are fixed one. These are the fixed one is component of y1, y2 up to yn, and say w1 up to wn. Okay, so if we subtract these 2 points, this becomes a scalar one, and this is basically this vector is a constant vector. This vector is a constant vector. Okay, because these 2 points are fixed. Okay, so suppose this equation is suppose this equation is 5. Okay, so we can say that and thus uh, from equation 4 and 5, from equations 4 and this equation 5, we have this W minus Y is A transpose. So you can write it because this is a vector. Okay, this is A transpose, and here is X minus W, and that is greater or equals to 0. Or you can write this is A transpose X. This is greater or equals to A transpose W. Okay, suppose this is equation number 6 here. Okay, and moreover, also you have write what is the value of A transpose W minus Y. A transpose W minus Y. What is the value of this? So you know that A transpose, and W minus Y is a vector A. So this is A transpose A, and this is a constant vector. So this A transpose A is always greater than 0. Okay, or you say that what is the A transpose W is, or you can, this implies that A transpose this W minus Y. So you say that you find here A transpose W minus Y is greater than 0. Greater than 0 means this means you say that A transpose W is greater than A transpose Y. And this is question number 7. Okay, so here look at question number 6 and 7. 6 and 7 is A transpose X is greater or equals to A transpose W. And here A transpose W is strictly greater than A transpose Y. So from 6 and 7, so from equations 6 and 7, we get here this A transpose X is greater than okay, the next page next page A transpose X is greater or equals to A transpose W, and this is strictly greater than A transpose Y. So in next page, so A transpose X is greater or equals to A transpose W. This is equation number 6, and this is strictly greater than A transpose Y. This is equation number 7. Okay, so here you know that here you S in the set here uh, any given point Y. So see Y is known and W is also known. Okay, and here this vector is vector A. Okay, so A transpose, this is a constant vector, and Y be the given point. So if you multiply these two, A transpose into Y, so this be a real. Okay, so this means this A be the vector of Rn, and this A belongs to your Rn space, and of course y is also belongs to Rn space. Okay, so this means a vector is across n cross 1, and this is y with also n cross 1. A transpose is 1 cross n, and this is n cross 1. So this is becomes to 1 cross 1. That is a real number. Okay, so this is a real number, and if this real number, if we say that real number is b, okay, we say that that real number is b. Okay, so this means you have proved that thus for any x, just for any x which belongs to the closed convex set S, you have proved that this A transpose X, this is greater than this B. Okay, so you prove that this thing A transpose of X that equals to greater than B for any X which belongs to that set X. Okay, so this means which means that the convex set S that lies only in the open hub space, the open hub space that is A transpose X that is greater than B, and that hyperplane is produced by this thing. Okay, and this is your hyperplane H. Okay, and this is completely lie on the one of the hub spaces. Okay, so this A transpose X, this open half spaces, and that half spaces produced by the hyperplane by the hyperplane which is A transpose X that equals to B. Okay, so this is your hyperplane is produced by A transpose this A with a orthogonal vector. Okay, which passes through this point C. This equals to a B. Okay, so here the proof is complete. Okay, so this completes your proof.
हेलो सर,
Hmm.
कन्वेक्स सेट एस लाइज उसके बाद क्या लिखे हैं?
Lies wholly WHOLLY.
ओके सर.
Okay, so next theorem is supporting hyperplane. Okay, so supporting hyperplane theorem. So first of all, what is supporting hyperplane? Supporting hyperplane. So basically, if we take some convex set, okay, uh, non-empty. Basically, if we take okay, so we define here any hyperplane H, hyperplane. If we take that is H, and this is the collection of all X such that A transpose X equals to B. You know that what is the hyperplane formula. Okay, so this hyperplane H is called is is called a supporting hyperplane called uh, supporting hyperplane of any set S which is non-empty set in Rn. Okay, so this is a double neatly convex zero. Okay, this is non-empty set in Rn. Okay, so this hyperplane is called supporting hyperplane of this non-empty set S at any point at if you take suppose at point W, which is basically the that point is boundary point, that is boundary point of your non-empty set S. If if this A transpose W that equals to B, and S is contained in either in the half space, there in the half space A transpose X is less or equals to B, or in the other half space, or in the half space A transpose X is greater or equals to B. Okay, so that hyperplane S is said to be supporting hyperplane. Okay, so if we take any set, so suppose if we take this type of polygon, if you take this is your polygon, okay, and of course this is a convex, non-empty convex set. Okay, so here we take a hyperplane which passes through this point, this point. Okay, so this is your supporting hyperplane. Okay, if we take a non-empty, non-convex set, suppose if we take this type of set, this type of set, okay, this is a non-convex, but this is non-empty set. Okay, so in this case, there is a supporting hyperplane which basically it passes through this and touches at any point. Okay, this means this is जो supporting hyperplane H. Okay, so किसी भी सेट में जो उसके एक तरह से टेंजेंशियल होके जाए, टच करते हुए किसी एक पॉइंट से टच होके जाए, और वो पॉइंट जो है वो दैट इज contained in this set F, and that point is your boundary point of F. Okay, तो इस तरह का जो भी होगा हम उससे हम कहेंगे कि that is your hyperplane, and that hyperplane is supporting hyperplane. और आप ये देख रहे हैं कि S जो है या तो ये जो से डिवाइड कर रहे हैं, तो यहाँ पे आपको टू हाफ स्पेसेस होंगी, एक ये हाफ स्पेस है, सेकंड वन दिस हाफ स्पेसेस. ओके, सेकंड वन दिस हाफ स्पेसेस. तो इसमें ये कह रहे हैं कि ये जो है दिस इज एस जो है कंप्लीटली जो है दिस इज लेस और इक्वल्स टू, मींस इसमें जो क्लोज्ड हम ले रहे हैं क्लोज हाफ स्पेस है, इसमें कंप्लीटली इसमें या इसमें किसी एक में होगा. उसी तरह से ये एच है हाइपरप्लेन, ये आपने इसको कंप्लीटली टू में डिवाइड कर दिया, बट एस इज कंटेन्ड इन either this half space or this half space. Similarly, if you take ऐसा भी पॉसिबल है कि किसी ऐसा भी नॉन एम्प्टी सेट मिल सकता है जहाँ पे हमारे दो बाउंड्री पॉइंट को टच करता हुआ ये जाए. Okay? तो अगर आप सपोज इस टाइप का अगर हमने कुछ ले लिया, सपोज दिस इज योर S, okay, which is a non-convex set, and here if you take hyperplane like that, okay, this touches 2 point. Okay, so this is also supporting hyperplane, and that divides this region into half spaces, and this set S is completely lying in one of the closed half spaces. Okay, तो ऐसे भी सपोर्टिंग हाइपरप्लेन है जो कि इसके वर्टेक्स से जाएं, या फिर एक ही पॉइंट किसी पॉइंट पर टेंजेंशियल होके जाए, या फिर ऐसे भी हो सकते हैं कि यहाँ पे आपको ऐसे पॉइंट्स मिल सकते हैं जहाँ से टच होकर के जाएं, या फिर आपको इन्फिनिट नंबर ऑफ पॉइंट्स भी मिल सकते हैं. सपोज इफ यू टेक दिस टाइप ऑफ S, okay, this type of S, and we take if you take suppose ऐसा अगर आपने हाइपरप्लेन लिया तो सिंपली एक वर्टेक्स से हो जाएगा, लेकिन अगर हमने एक इस तरह का एक हाइपरप्लेन ले लिया, इस तरह का हाइपरप्लेन लिया, दैट इज योर H. Okay, so this touches infinite number of points, so this is your supporting hyperplane. Okay, तो ये भी आपके supporting hyperplane. This completely divides your spaces in two half spaces, first one upper and second one lower, and S is completely lying in one of them. Okay, तो ये आपके कई स्ट्रक्चर्स हैं, आप इस तरह से डिफाइन कर सकते हैं अपने supporting hyperplanes. Okay, and these all are H are basically this H is supporting hyperplane. This H is supporting hyperplane. Okay. And that hyperplane is defined by the formula A transpose x that equals to B. And this x is lies between any one of A transpose x is lesser equals to B here, where A transpose x is lesser equals to B here, A transpose x lesser equals to B here. Okay, तो जैसा भी आप ले सकते हैं, A transpose x is lesser equals to B here. Okay, where A with a this vector. So these are some examples of supporting hyperplane. So now we go to the theorem that is known by the supporting hyperplane theorem. Okay, so what is that? Next page. Next page. Theorem. And this theorem is supporting hyperplane theorem. Okay. So this theorem says that if we assume that any S be a closed complex set, be a closed complex set in Rn space, and let the point, the boundary point W, be a boundary point of that convex set, point of that convex set S, then there exists, then there exists at least one supporting hyperplane, at least there exists at least at least one supporting hyperplane of S at the point W. Okay, so here we try to prove this theorem, and this theorem is based on separating hyperplane theorem. Okay, तो इसको हम प्रूव करेंगे. ये टाइम 6 मिनट ही है, तो हम देखते हैं, कोशिश करते हैं जल्दी से करने. So proof. So here we assume that W be any boundary point of your set S, and if we take this set is basically S, okay, and we take this W be any boundary point of this, and we take any point say which is yk, okay, yk, which is not in that set S. Okay, so and this point yk is basically in some neighborhood of this point wk. So we say that this is a basically epsilon k, where epsilon k that equals 1 by k, neighborhood of this set w. Okay, तो चलिए हम इसको हम नेक्स्ट टर्म पे करते हैं. या आपके पास अभी फ्री हैं, 10 मिनट्स हैं आपके पास? क्या है आपका पोजीशन? नेक्स्ट क्लास कब है?
सर आज नहीं है कोई अब क्लास.
कोई क्लास नहीं, तो हम 10 मिनट एक्स्ट्रा ले लें आपकी ना. ठीक. Okay,
Yes.
okay, okay. So now we should assume that here uh, yk be a point, yk be a point, and that point not in your set S. Okay, but but in the some neighborhood of, in the say epsilon k neighborhood of, that epsilon k means if we take what is the value of epsilon k. So if we take this epsilon k, that is 1 by k. Okay, if we say, so we take this neighborhood of this point w, that point is your boundary point. Okay, so by previous theorem, that is separating hyperplane theorem, by separating hyperplane theorem, there you know that there is a boundary point, there is a boundary point, there is a boundary point, say wk of s, whose distance is, whose distance from this point yk is minimal. Okay, so this means if you take this yk point, so here corresponding to this yk, you have a minimum distance of that. Suppose this point is wk. Okay, so for different points, suppose if you take different points here, 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 here. If you take y1 point, this is one epsilon neighborhood of, let's say, w1, then w2, w3, w4. So we goes to here, and we take the different points. Okay, for different yk, k1, 2, 3 up to infinity. Okay, where that infinite number of y1, y2 up to yk point is not in S, we get a different points w1, w2 up to wk on this set S, that distance is minimum one. Okay, so and if you assume that there is basically at any point of this wk, there is hyperplane which passes through that wk, and that is a ak transpose x, that equals to pk. Okay, so here we say that from our supporting hyperplane theorem, so we know that the distance between this wk minus your normal point, boundary point w, this equals to, you can write this is in the form of wk. If we adding and subtracting this arbitrary point outside of that convex set S, if we adding that point and subtracting that point, okay, minus w. So this value is, we know that this is less or equals to, this is less or equals to norm of this wk minus of yk plus norm of this yk minus w. Okay, and suppose this is your equation number 1. Okay, and you also know that the norm of this yk minus w, this yk minus w, and this yk point is basically the epsilon k neighborhood of this point yk, is basically epsilon k neighborhood of this boundary point wk. So this means this is less than your epsilon. Okay, because you take the epsilon neighborhood of that point, you can say this is epsilon k. Okay, and here you also know that this epsilon k, that equals to 1 is 1 by k. When k tends to very large, when it tends to infinity, this epsilon k, this equals to 0. So this means you say that this norm of yk minus w is tends to 0 as this k is very large. Okay, And further, since this norm of wk minus yk, okay, this is basically the shortest distance between k, because for every k you find a wk which belongs to this s, and that distance is minimum one. So that's why this wk, this distance is the smallest distance, the smallest distance yk and s. This is the smallest distance. So therefore, this the distance yk, this distance is the smallest one. This is also less or equals to this, the distance between these 2 points. This means yk and your boundary point w. This is also less than this thing. And uh, here you show that this yk minus w norm on that is tends to zero as k tends to very large. So this is also tends to zero as k tends to infinity. Okay, so you say that from equation one, so you can say that from equation first, this norm of wk minus w, this is less or equals to norm of this wk minus yk plus yk minus w, and this wk minus yk, this wk minus yk is tends to zero as k tends to infinity, and yk minus w is also tends to zero as k tends to infinity. This implies this tends to zero as uh, k tends to infinity. Okay, so from equation one, we say that this wk minus w, this is tends to zero as k tends to infinity. Or you say that your wk tends to your boundary point, and that boundary point is your w. Okay, so now if we take for each w1, w2, w3, wk, at each point, if we suppose there are certain hyperplanes at different points, and that hyperplane is governed by the formula that is A transpose AK for different, we have different vectors. So A transpose X, that is equals to BK at uh, the different points post WK. Okay, so now if we divide both sides of supporting hyperplane, so on next page, so now dividing both sides of the supporting hyperplane, supporting hyperplane, that is A transpose K X is equals to BK at the point WK by the length of this vector, and length of that vector is AK. So we get here this, if we write in AK bar transpose X, this equals to the form of BK bar, or what is the value of barring here? Here barring means we're dividing the magnitude of that mod of AK. Okay, so here we're dividing AK vector, what is the value of AK bar is equals to vector AK norm of AK, and what is the value of BK bar? So BK bar is basically your vector BK norm of BK. Okay, so here, so this is equation number two. And here, if we take what is the norm of this AK bar, so that we take the norm of AK bar, so this equals to, what is the value of AK bar? AK bar is equals to AK upon norm of AK. So this equals to AK bar. This equals to norm of, what is the value of AK over norm of AK. So this equals to 1. Okay, so here you prove that here your sequence basically a1 a2 up to a infinity there are the sequence ak bar. This is bounded, so it has